So in this video and the next, we're going to study a very cool divide and conquer algorithm for the closest pair problem. This is a problem where you're given endpoints in the plane and you want to figure out which pair of points are closest to each other. So this will be the first taste we get of an application in computational geometry, which is the part of algorithms which studies how to reason and manipulate geometric objects. So those algorithms are important in, among other areas, robotics, computer vision, and computer graphics. So this is relatively advanced material. It's a bit more difficult than the other applications of divide and conquer that we've seen. The algorithm's a little bit tricky, and it has a quite non-trivial proof of correctness. So just be ready for that, and also be warned that because it's more advanced, I'm going to talk about the material at a slightly faster pace than I do in most of the other videos. So let's begin now by defining the problem formally. So we're given as endpoints in the plane, so each one just defined by its x-coordinate and its y-coordinate. And when we talk about the distance between 2 points in this problem, we're going to focus on Euclidean distance. So let me remind you what that is briefly, but we'll introduce some simple notation for that, which we'll use for the rest of the lecture. So we're just going to note the Euclidean distance between 2 points pi and pj by d of pi pj. So in terms of the x and y coordinates of these 2 points, we just look at the squared differences in each coordinate, sum them up, and take the square root. And now, as the name of the problem would suggest, the goal is to identify among all pairs of points that pair which has the smallest distance between them. Next, let's start getting a feel for the problem by making some preliminary observations. First, I want to make an assumption, purely for convenience, that there's no ties. So that is, I'm going to assume all endpoints have distinct x-coordinates, and also all endpoints have distinct y-coordinates. It's not difficult to extend the algorithm to accommodate ties. I'll leave it to you to think about how to do that. So next, let's draw some parallels with the problem of counting inversions, which was an earlier application of divide and conquer that we saw. The first parallel I want to point out is that if we're comfortable with a quadratic time algorithm, then this is not a hard problem. We can simply solve this by brute force search. And again, by brute force search, I just mean we set up a double for loop, which iterates over all distinct pairs of points. We compute the distance for each such pair, and we remember the smallest. That's clearly a correct algorithm. It has to iterate over a quadratic number of pairs, so its running time is going to be theta of n squared. And as always, the question is, can we apply some algorithmic ingenuity to do better? Can we have a better algorithm than this naive one which iterates over all pairs of points? You might have an initial instinct that because the problem asks about a quadratic number of different objects, perhaps we fundamentally need to do quadratic work. But again, recall back in counting inversions, using divide and conquer, we were able to get an n log n algorithm, despite the fact that there might be as many as a quadratic number of inversions in an array. So the question is, can we do something similar here for the closest pair problem? Now, one of the keys to getting an n log n time algorithm for counting inversions was to leverage a sorting subroutine. Recall that we piggybacked on merge sort to count the number of inversions in n log n time. So the question is, here, with the closest pair problem, perhaps sorting again can be useful in some way to beat the quadratic barrier. So to develop some evidence that sorting will indeed help us compute the closest pair of points and better than quadratic time, let's look at a special case of the problem, really an easier version of the problem, which is when the points are just in one dimension, so on the line, rather than in 2 dimensions in the plane. So in the 1D version, all of the points just lie on a line like this one, and we're given the points in some arbitrary order, not necessarily in sorted order. So, a way to solve the closest pair problem in 1 dimension is to simply sort the points, and then of course the closest pair better be adjacent in this ordering, so you just iterate through the n-1 consecutive pairs and see which one is closest to each other. So more formally, here's how you solve the 1-dimensional version of the problem. You sort the points according to their only coordinate, because again, remember this is 1 dimension. So as we've seen using merge sort, we can sort the points in n log n time. And then we just do a scan through the points, so this takes linear time, and for each consecutive pair we compute their distance and we remember the smallest of those consecutive pairs and we return that. That's got to be the closest pair. So in this picture on the right, I'm just going to circle here in green the closest pair of points. So this is something we discover by sorting and then doing a linear scan. Now, needless to say, this isn't directly useful. This is not the problem I started out with. We wanted to find the closest pair among points in the plane, not points in the line. But I want to point out that even in the line, there are a quadratic number of different pairs, so brute force search is still a quadratic time algorithm, even in the 1D case. So at least with 1 dimension, we can use sorting, piggyback on it, to beat the naive brute force search bound and solve the problem in n log n time. So our goal for this lecture is going to be to devise an equally good algorithm for the 2-dimensional case. So we want to solve closest pair of points in the plane, again in n log n time. So we will succeed in this goal. I'm going to show you an n log n time algorithm for 2D closest pair. It's going to take us a couple steps. So let me begin with the high-level approach. All right, so the first idea to try is just to copy what worked for us in the one-dimensional case. So in the one-dimensional case, we first sorted the points by their coordinate, and that was really useful. Now in the 2D case, points have two coordinates, x coordinates and y coordinates, so there's two ways to sort them. So let's just sort them both ways. That is, the first step of our algorithm, which you should really think of as a pre-processing step. We're going to take the input points, we invoke merge sort once to sort them according to x coordinate, that's one copy of the points, and then we make a second copy of the points where they're sorted by y coordinate. So we're going to call those copies of points px, that's an array of the points sorted by x coordinate, and py for them sorted by y coordinate. Now we know merge sort takes n log n time, so this pre-processing step only takes O of n log n time. And again, given that we're shooting for an algorithm with running time big O of n log n, why not sort the points? We don't even know how we're going to use this fact right now, but it's sort of harmless. It's not going to affect our goal of getting a big of O of n log n time algorithm. And indeed, this illustrates a broader point, which is one of the themes of this course. So recall, I hope one of the things you take away from this course is a sense for what are the four free primitives. What are manipulations or operations you can do on data, which basically are costless, meaning that if your data set fits in the main memory of your computer, you can basically invoke the primitive and it's just going to run blazingly fast. And you can just do it even if you don't know why. And again, sorting is the canonical for free primitive, although we'll see some more later in the course. And so here we're using exactly that principle. So we don't even understand why yet we might want the points to be sorted. It just seems like it's probably going to be useful, motivated by the 1D case. So let's go ahead and make sorted copies of the points by x and y coordinate up front. So reasoning by analogy with the 1D case suggests that sorting the points might be useful, but we can't carry this analogy too far. So in particular, we're not going to be able to get away with just a simple linear scan through these arrays to identify the closest pair of points. So to see that, consider the following example. So we're going to look at a point set which has 6 points. There's going to be 2 points, which I'll put in blue, which are very close in x coordinate, but very far away in y coordinate. And then there's going to be another pair of points, which I'll do in green, which are very close in y coordinate, but very far away in x coordinate. And then there's going to be a red pair of points, which are not too far away in either the x coordinate or the y coordinate. So in this set of 6 points, the closest pair is the pair of red points, but they're not even going to show up consecutively in either of the two arrays, right? So in the array that's sorted by x coordinate, this blue point here is going to be wedged in between the 2 red points. They won't be consecutive. And similarly in py, which is sorted by y coordinate, this green point is going to be wedged between the 2 red points. So you won't even notice these red points if you just do a linear scan through px and py and look at the consecutive pairs of points. So following our pre-processing step where we just invoke merge sort twice, we're going to do a quite non-trivial divide and conquer algorithm to compute the closest pair. So really in this algorithm, we're applying the divide and conquer algorithm twice. First, internal to the sorting subroutine, assuming that we use the merge sort algorithm to sort, divide and conquer is being used there to get an n log n running time in this pre-processing step, and then we're going to use it again on the sorted arrays in a new way, and that's what I'm going to tell you about next. So let's just briefly review the divide and conquer algorithm design paradigm before we apply it to the closest pair problem. So as usual, the first step is to figure out a way to divide your problem into smaller subproblems. Sometimes this has a reasonable amount of ingenuity, but it's not going to here in the closest pair problem. We're going to proceed exactly as we did in the merge sort and counting inversions problems, where we took the array and broke it into its left and right half. So here we're going to take the input point set and again just recurse on the left half of the points and recurse on the right half of the points. We're here by left and right, I mean with respect to the points x coordinates. There's pretty much never any ingenuity in the conquer step. That just means you take the subproblems you identified in the first step and you solve them recursively. That's what we'll do here. We'll recursively compute the closest pair in the left half of the points and the closest pair in the right half of the points. So where all the creativity in divide and conquer algorithms lie is in the combined step. Given solutions to your subproblems, how do you somehow recover a solution to the original problem, the one that you actually care about? So for closest pair, the question is going to be, given that you've computed the closest pair on the left half of the points, the closest pair on the right half of the points, how do you then quickly recover the closest pair from the whole point set? That's a tricky problem. That's what we're going to spend most of our time on. So let's make this divide and conquer approach for closest pair a little bit more precise. So let's now actually start spelling out our closest pair algorithm. The input we're given, this follows the pre-processing step. So recall that we invoke merge sort twice. We get our 2 sorted copies of the point set px sorted by x coordinate and py sorted by y coordinate. So the first step then is the division step. So given that we have a copy of the points px sorted by x coordinate, it's easy to identify the leftmost half of the points, those with those n over 2 smallest x coordinates, and then the right half, those with the n over 2 largest x coordinates. We're going to call those q and r respectively. One thing I'm skipping over is the base case. I'm not going to bother writing that down. So base case omitted, but it's what you would think it would be. So basically, once you have a small number of points, say 2 points or 3 points, then you can just solve the problem in constant time by brute force search. You just look at all the pairs and you return the closest pair. So think of there being at least 4 points in the input. Now, in order to recurse, to call closest pair again on the left and right halves, we need sorted versions of Q and R, both by X coordinate and by Y coordinate. So we're just going to form those by doing suitable linear scans through PX and PY. And so one thing I encourage you to think through carefully, or maybe even code up after the video, is how would you form QX, QY, RX, and RY, given that you already have PX and PY. And if you think about it, because PX and PY are already sorted, just producing these sorted sublists takes linear time. It's in some sense the opposite of the merge subroutine we used in merge sort. Here we're sort of splitting rather than merging. But again, this can be done in linear time. That's something you should think through carefully later. So that's the division step. Now we just conquer, meaning we recursively call closest pair on each of the two subproblems. So when we invoke closest pair on the left half of the points on Q, we're going to get back what are indeed the closest pair of points amongst those in Q. So we're going to call those P1 and PQ. So among all pairs of points that both lie in Q, P1 and Q1 minimize the distance between them. Similarly, we're going to call P2, Q2 the results of the second recursive call. That is, P2 and Q2 are amongst all pairs of points that both lie in R, the pair that has the minimum Euclidean distance. Now conceptually there's two cases. There's a lucky case and there's an unlucky case. In the original point set P, if we're lucky, the closest pair of points in all of P, actually both of them lie in Q or both of them lie in R. In this lucky case, we'd already be done. If the closest pair in the entire point set, they happen to both lie in Q, then this first recursive call is going to recover them, and we just have them in our hands, P1, Q1. Similarly, if both of the closest pair of points in all of P lies on the right side, in R, then they get handed to us on a silver platter by the second recursive call that just operates on R. So in the unlucky case, the closest pair of points in P happens to be split. That is, one of the points lies in the left half in Q, and the other point lies in the right half in R. Notice, if the closest pair of points in all of P is split, is half in Q and half in R, neither recursive call is going to find it. Okay? The pair of points is not passed to either of the two recursive calls, so there's no way it's going to be returned to us. Okay? So we have not identified the closest pair after these two recursive calls if the closest pair happens to be split. This is exactly analogous to what happened when we were counting inversions. The recursive call in the left half of the array counted the left inversions. The recursive call in the right half of the array counted the right inversions, but we still had to count the split inversions. So in this closest pair algorithm, we still need a special purpose subroutine that computes the closest pair for the case in which it is split, in which there's 1 point in Q and 1 point in R. So just like in counting inversions, I'm going to write down that subroutine and I'm going to leave it unimplemented for now. We'll figure out how to implement it quickly in the rest of the lecture. Now, if we have a correct implementation of closest split pair, so that takes as input the original point set sorted by X and Y coordinate and returns the smallest pair that's split, where 1 point's in Q and 1 point's in R, then we're done. So then the closest pair has to either be on the left or on the right, or it has to be split. Steps 2 through 4 compute the closest pair in each of those categories. So those are the only possible candidates for the closest pair, and we just return the best of them. So that's an argument for why, if we have a correct implementation of the closest split pair subroutine, then that implies a correct implementation of closest pair. Now, what about the running time? So the running time of the closest pair algorithm is going to be in part determined by the running time of closest split pair. So in the next quiz, I want you to think about what kind of running time we should be shooting for with the closest split pair subroutine. So the correct response to this quiz is the second one. And the reasoning is just by analogy with our previous algorithms for merge sort and for counting inversions. So what is all of the work that we would do in this algorithm? Well, we do have this pre-processing step we call merge sort twice. We know that's n log n, so we're not going to have a running time better than n log n because we sort at the beginning. And then we have a recursive algorithm with the following flavor. It makes 2 recursive calls. Each recursive call is on a problem of exactly half the size with half the points of the original one. And outside of the recursive calls, by assumption, in the problem, we do a linear amount of work in computing the closest split pair. So the exact same recursion tree, which proves an n log n n bound for merge sort, proves an n log n bound for how much work we do after the pre-processing step. So that gives us an overall running time bound of n log n. And remember, that's what we were shooting for. We were working n log n already to solve the one-dimensional version of closest pair, and the goal of these lectures is to have an n log n algorithm for the 2D version. So this would be great. So in other words, the goal should be to have a correct linear time implementation of the closest split pair subroutine. If we can do that, we're home free. We get the desired n log n algorithm. Now, I'm going to proceed in a little bit to show you how to implement closest split pair, but before I do that, I want to point out one subtle but key idea, which is going to allow us to get this linear time correct implementation. So let me just put that on this slide. So the key idea is that we don't actually need a full-blown correct implementation of the closest split pair subroutine. So I'm not actually going to show you a linear time subroutine that always correctly computes the closest split pair of a point set. The reason I'm not going to do that is that's actually a strictly harder problem than what we need to have a correct recursive algorithm. We do not actually need a subroutine that, for every point set, always correctly computes the closest split pair of points. Remember, there's a lucky case and there's an unlucky case. The lucky case is where the closest pair in the whole point set P happens to lie entirely in the left half of the points Q or in the right half of the points R. In that lucky case, one of our recursive calls will identify this closest pair and hand it over to us on a silver platter. We could care less about the split pairs in that case. We get the right answer without even looking at the split pairs. Now there's this unlucky case where the split pair happens to be the closest pair of points. That is when we need this linear time subroutine, and only then, only in the unlucky case where the closest pair of points happens to be split. Now that's in some sense a fairly trivial observation, but there's a lot of ingenuity here in figuring out how to use that observation, the fact that we only need to solve a strictly easier problem, and that will enable the linear time implementation that I'm going to show you next. So now let's rewrite the high-level recursive algorithm slightly to make use of this observation that the closest split pair subroutine only has to operate correctly in the regime of the unlucky case, when in fact the closest split pair is closer than the result of either recursive call. So I've erased the previous steps 4 and 5, but we're going to rewrite them in a second. So before we invoke closest split pair, what we're going to do is we're going to see how well did our recursive calls do. That is, we're going to define a parameter little delta, which is going to be the closest pair that we found, or the distance of the closest pair we found by either recursive call. So the minimum of the distance between P1 and Q1, the closest pair that lies entirely on the left, and P2, Q2, the closest pair that lies entirely on the right. Now we're going to pass this delta information as a parameter into our closest split pair subroutine. We're going to have to see why on earth that would be useful. I still owe you that information, but for now we're just going to pass delta as a parameter for use in closest split pair. And then as before, we just do a comparison between the 3 candidate closest pairs and return the best of the trio. And so just so we're all clear on where things stand, so what remains is to describe the implementation of closest split pair. And before I describe it, let me just be crystal clear on what it is that we're going to demand of this subroutine. What do we need to have a correct and O of n log n time closest pair algorithm? Well, as you saw in the quiz, we want the running time to be O of n always. And for correctness, what do we need? Again, we don't need it to always compute the closest split pair, but we need it to compute the closest split pair in the event that there is a split pair of distance strictly less than delta, strictly better than the outcome of either recursive call. So now that we're clear on what we want, let's go ahead and go through the pseudocode for this closest split pair subroutine. And I'm going to tell you up front, it's going to be fairly straightforward to figure out that the subroutine runs in linear time, O of n time. The correctness requirement of closest split pair will be highly non-obvious. In fact, after I show you the pseudocode, you're not going to believe me. You're going to look at the pseudocode and you're going to be like, what are you talking about? But in the second video on the closest pair lecture, we will in fact show that this is a correct subroutine. So how does it work? Well, let's look at a point set. So the first thing we're going to do is a filtering step. We're going to prune a bunch of the points away and sort of zoom in on a subset of the points. And the subset of the points we're going to look at is those that lie in a vertical strip, which is roughly centered in the middle of the point set. So here's what I mean. By centered, we're going to look at the middle x-coordinate. So let x bar be the biggest x-coordinate in the left half. So that is, in the sorted version of the points by x-coordinate, we look at the n over 2th smallest x-coordinate. So in this example where we have 6 points, all this means is we imagine drawing a line between the third point. So that's going to be x bar, the x-coordinate of the third point from the left. Now, since we're passed as input a copy of the points sorted by x-coordinate, we can figure out what x bar is in constant time, just by accessing the relevant entry of the array px. Now, the way we're going to use this parameter delta that we're passed, so remember what delta is. So before we invoke the closest split pair subroutine in the recursive algorithm, we make our 2 recursive calls. We find the closest pair on the left, the closest pair on the right, and delta is whatever the smaller of those 2 distances are. So delta is the parameter that controls whether or not we actually care about the closest split pair or not. We care if and only if there is a split pair at distance less than delta. So how do we use delta? Well, that's going to determine the width of our strip. So the strip's going to have width 2 delta, and it's going to be centered around x. And the first thing we're going to do is we're going to ignore forevermore points which do not lie in this vertical strip. So the rest of the algorithm will operate only on the subset of p, the subset of the points that lie in this strip. And we're going to keep track of them sorted by y-coordinate. So the formal way to say that they lie in this strip is that they have x-coordinate in the interval with lower endpoint x bar minus delta and upper endpoint x bar plus delta. Now, how long does it take to construct this set sy sorted by y-coordinate? Well, fortunately, we've been passed as input a sorted version of the points py. So to extract sy from py, all we need to do is a simple linear scan through py, checking for each point where its x-coordinate is. So this can be done in linear time. Now, I haven't yet shown you why it's useful to have this sorted set sy, but if you take it on faith that it's useful to have the points in this vertical strip sorted by y-coordinate, you now see why it was useful that we did this merge sort all the way at the beginning of the algorithm, before we even underwent any recursion. Remember, what is our running time goal for closest split pair? We want this to run in linear time. That means we cannot sort inside the closest split pair subroutine. That would take too long. We want this to be linear time. Fortunately, since we sorted once and for all at the beginning of the closest pair algorithm, extracting sorted sublists from those sorted lists of points can be done in linear time, which is within our goals here. Now, it's the rest of the subroutine where you're never going to believe me that it does anything useful. So I claim that essentially with a linear scan through sy, we're going to be able to identify the closest split pair of points in the interesting, unlucky case where there is such a split pair with distance less than delta. So here's what I mean by that linear scan through sy. So as we do the scan, we're going to keep track of the closest pair of points of a particular type that we've seen so far. So let me introduce some variables to keep track of the best candidate we've seen so far. So there's going to be a variable best, which will initialize to be delta. Remember, we're uninterested in split pairs unless they have distance strictly less than delta. And then we're going to keep track of the points themselves, so we'll initialize the best pair to be null. Now here's the linear scan. So we go through the points of sy in order of y-coordinate. Okay, well, not quite all the points of sy. We stop at the 8th to last point, and you'll see why in a second. And then for each position I of the array sy, we investigate the 7 subsequent points of this same array sy. So for j going from 1 to 7, we look at the ith and I plus jth entry of sy. So if sy looks something like this array here, at any given point in this double for loop, we're generally looking at an index I, a point in this ith entry of the array, and then some really quite nearby point in the array I plus j, because j here is going to be at most 7. Okay, so we're constantly looking at pairs in this array, but we're not looking at all pairs at all. We're only looking at pairs that are very close to each other within 7 positions of each other. And what do we do for each choice of I and j? Well, we just look at those points, we compute the distance, we see if it's better than all of the pairs of points of this form that we've looked at in the past, and if it is better, then we remember it. So we just remember the best, i.e. closest pair of points of this particular type for choices of I and j of this form. So in more detail, if the distance between the current pair of points p and q is better than the best we've seen so far, we reset the best pair of points to be equal to p and q, and we reset the best distance, the closest distance seen so far, to be the distance between p and q. And that's it. Then once this double for loop terminates, we just return the best pair. So one possible execution of closest split pair is that it never finds a pair of points p and q with distance less than delta. In that case, this is going to return null, and then in the outer call, in the closest pair, obviously you interpret a null pair of points to having infinite distance. So if you call closest split pair and it doesn't return any points, then the interpretation is that there's no interesting split pair of points, and you just return the better of the results of the two recursive calls, p1, q1 or p2, q2. Now, as far as the running time of this subroutine, what happens here? Well, we do constant work, just initializing the variables. Then notice that the number of points in sy, well, in the worst case, you have all of the points of p, so there's going to be at most n points. And so you do a linear number of iterations in the outer for loop. But here's the key point. In the inner for loop, right, normally double for loops give rise to quadratic running time, but in this inner for loop, we only look at a constant number of other positions. We only look at 7 other positions. And for each of those 7 positions, we only do a constant number of work, right? We just compare distance and make a couple other comparisons and reset some variables. So for each of the linear number of outer iterations, we do a constant amount of work, so that gives us a running time of O of n for this part of the algorithm. So as I promised, analyzing the running time of this closest split pair subroutine was not challenging. We just, in a straightforward way, looked at all the operations. And again, because in the key linear scan we only do constant work per index, the overall running time is big O of n, just as we wanted. So this does mean that our overall recursive algorithm will have running time O of n log n. What is totally non-obvious, and perhaps even unbelievable, is that this subroutine satisfies the correctness requirements that we wanted. And remember what we needed that whenever we're in the unlucky case, whenever in fact the closest pair of points in the whole point set is split, this subroutine better find it. So, but it does, and that's made precise in the following correctness claim. So let me phrase the claim in terms of an arbitrary split pair which has distance less than delta, not necessarily the closest such pair. So suppose there exists a point on the left side and a point on the right side, so that is a split pair. And suppose the distance of this pair is less than q. Now there may or may not be such a pair of points pq. Don't forget what this parameter delta means. What delta is, by definition, is the minimum of d of p1 q1, where p1 q1 is the closest pair of points that lie entirely in the left half of the point set q, and d of p2 q2, where similarly p2 q2 is the closest pair of points that lies entirely on the right inside of R. So if there's a split pair with distance less than delta, this is exactly the unlucky case of the algorithm. This is exactly where neither recursive call successfully identifies the closest pair of points. Instead, that closest pair is a split pair. On the other hand, if we are in the lucky case, then there will not be any split pairs with distance less than delta, because the closest pair lies either all on the left or all on the right, and it's not split. But remember, so we're interested in the case where there is a split pair that has distance less than delta, where there is a split pair that is the closest pair. So the claim has two parts. The first part, part A, says the following. It says that if there's a split pair P and Q of this type, then P and Q are members of SY. Now let me just sort of redraw the cartoon. So remember what SY is. SY is that vertical strip. And again, the way we got that is we drew a line through a median x coordinate, and then we fattened it by delta on either side, and then we focused only on points that lie in the vertical strip. Now notice our counts split pair subroutine, if it ever returns a pair of points, it's going to return a pair of points PQ that belong to SY. First it filters down to SY, then it does a linear search through SY. So if we want to believe that our subroutine identifies best split pairs of points, then in particular such split pairs of points better show up in SY. They better survive the filtering step. So that's precisely what part A of the claim is. Here's part B of the claim, and this is the more remarkable part of the claim, which is that P and Q are almost next to each other in this sorted array SY. So they're not necessarily adjacent, but they're very close. They're within 7 positions away from each other. So this is really the remarkable part of the algorithm. This is really what's surprising and what makes the whole algorithm work. So just to make sure that we're all clear on everything, let's show that if we prove this claim, then we're done. Then we have a correct, fast implementation of a closest pair algorithm. I certainly owe you the proof of the claim. That's what the next video is going to be all about. But let's show that if the claim is true, then we're home free. So if this claim is true, then so is the following corollary, which I'll call corollary 1. So corollary 1 says, if we're in the unlucky case that we discussed earlier, if we're in the case where the closest point in the whole point set P does not lie both on the left, does not lie both on the right, but rather has one point on the left and one on the right, that is, it's a split pair, then in fact the count split pair subroutine will correctly identify the closest split pair, and therefore the closest pair overall. Why is this true? Well, what does count split pair do? Okay, so it has this double for loop, and it thereby explicitly examines a bunch of pairs of points, and it remembers the closest pair of all of the pairs of points that it examines. What does this, so what are the criteria that are necessary for a count split pair to examine a pair of points? Well, first of all, the points P and Q both have to survive the filtering step and make it into the array SY, right? So count split pair only searches over the array SY. Secondly, it only searches over pairs of points that are almost adjacent in SY, that are only 7 positions apart. But amongst pairs of points that satisfy those two criteria, count split pair will certainly compute the closest such pair, right? It just explicitly remembers the best of them. Now, what's the content of the claim? Well, the claim is guaranteeing that every potentially interesting split pair of points, namely every split pair of points with distance less than delta, meets both of the criteria which are necessary to be examined by the count split pair subroutine. So first of all, and this is the content of part A, if you have an interesting split pair of points with distance less than delta, then they'll both survive the filtering step. They'll both make it into the array SY. Part A says that. Part B says they're almost adjacent in SY. So if you have an interesting split pair of points, meaning it has distance less than delta, then they will in fact be at most 7 positions apart. Therefore, count split pair will examine all such split pairs, all split pairs with distance less than delta, and just by construction it will compute the closest pair of all of them. So again, in the unlucky case where the best pair of points is a split pair, then this claim guarantees that the count split pair will compute the closest pair of points. Therefore, having handled correctness, we can just combine that with our earlier observations about running time, and corollary 2 just says, if we can prove the claim, then we have everything we wanted. We have a correct O of n log n implementation for the closest pair points. So with further work and a lot more ingenuity, we've replicated the guarantee that we got just by sorting for the one-dimensional case. Now again, these corollaries hold only if the claim is in fact true. And I've given you no justification for this claim, and indeed even the statement of the claim I think is a little bit shocking. So if I were you, I would demand an explanation for why this claim is true, and that's what I'm going to give you in the next video.